In an exciting development for space exploration, citizen scientists are stepping into the limelight utilizing NASA's Open Science Data Repository (OSDR) to unravel the mysteries of life beyond Earth. This initiative invites volunteers from diverse backgrounds to contribute to groundbreaking research aimed at understanding how life can thrive in the challenging environments of deep space. As we continue to push the boundaries of our cosmic exploration, the role of citizen scientists becomes increasingly vital. Launched by the Analysis Working Group's AWGs within the OSDR, this project emphasizes collaboration and accessibility. The AWGs focus on a variety of critical topics, including the effects of radiation, the impact of microgravity on human and plant health, and how microbes adapt to the unique conditions of orbit. Currently, 9 distinct AWGs are operational, each hosting monthly meetings to discuss their specific focus areas and advance research efforts. Participants engage through an online platform known as the AWG Forum Space, where they can connect with peers and experts, join discussions, and contribute to over 20 active projects. The OSDR houses a wealth of data encompassing physiological studies, molecular biology, and bioimaging, among many other fields. For those new to the initiative, comprehensive tutorials and resources are available to help familiarize them with the repository's extensive offerings, including a multi-study visualization portal and a dedicated radiation telemetry data portal, RadLab. Ryan Scott, the science lead for the Ames Life Sciences Data Archive, encourages those interested to join the citizen science movement. "We are on a quest to understand how life adapts to space environments," he stated. "This is a unique opportunity for anyone to contribute to a question that is essential for humanity's future in space." The collaborative nature of these groups allows for diverse perspectives and expertise to merge, creating a rich research environment. Participants are not merely passive observers; they can propose new projects, engage in data analysis, and even shape the standards for data collection and interpretation. This democratization of scientific inquiry not only enhances the research but also fosters a sense of community among participants. On April 17, a virtual event will provide an overview of the AWG's operations and encourage further participation. This initiative reflects NASA's commitment to open science and public engagement, aiming to harness the collective knowledge and enthusiasm of citizen scientists worldwide. As we look ahead, the implications of this research extend beyond academia. Understanding how life can thrive in space is crucial for future missions to Mars and beyond, where conditions are harsh and unpredictable. The findings from these citizen-led projects could pave the way for sustainable human presence on other planets, addressing fundamental questions about our place in the universe. In conclusion, as citizen scientists engage with NASA's open data, they are not just contributing to scientific knowledge, they are helping to shape the future of space exploration. With the upcoming virtual event, the momentum is likely to increase, inviting even more individuals to join this historic quest. As these projects evolve, they will undoubtedly yield insights that will inform our understanding of life in the cosmos and our ability to sustain it in environments far removed from Earth. In a landscape marked by significant changes in the scientific community, recent developments suggest a pivotal moment for bioscience research, particularly in the wake of the Trump administration's potential funding cuts. As the United States grapples with internal challenges, a notable exodus of discontented scientists is beginning to unfold, prompting discussions about the opportunities available in other countries, particularly the United Kingdom. Tony Barnett, a prominent figure in UK biosciences, has raised a clarion call in a recent letter published by The Guardian. He emphasized that the UK stands to benefit immensely from the migration of American bioscientists disillusioned by diminished support for critical research areas such as mRNA technology. Barnett argued that just as the 1930s saw a concerted effort to attract leading scientists to the UK, now is the opportune moment for the British government to implement initiatives aimed at recruiting these researchers. He posited that a strategic investment in this area could yield substantial returns, both in terms of advancing scientific knowledge and enhancing the UK's global standing in bioscience. As Barnett noted, this is a low-cost initiative with potential huge returns, suggesting that the UK could capitalize on decades of investment made by the US in bioscience research. The implications of this shift are profound, as it not only highlights the vulnerabilities within the US research ecosystem but also presents an opportunity for other nations to bolster their scientific communities. In tandem with these developments, public engagement and education around mRNA technology are gaining momentum. Johns Hopkins University recently hosted a screening of The Messenger, a story of mRNA, a documentary that chronicles the journey of mRNA technology and its revolutionary impact on medicine. The film features insights from Nobel laureates Katalin Karikó and Drew Weissman, who were instrumental in the development of mRNA vaccines. The screening was accompanied by a fireside chat aimed at fostering dialogue among scientists, policymakers, and the public, emphasizing the importance of building trust in science amid ongoing challenges. Moreover, the upcoming American Society for Biochemistry and Molecular Biology ASBMB 2025 annual meeting promises to spotlight key figures in the field, including Melissa Moore, a leading RNA biochemist and former chief scientific officer at Moderna. Her work has been pivotal in advancing mRNA-based therapeutics, and she is set to discuss the significance of effective science communication. Moore's evolution from groundbreaking research to public engagement underscores a growing recognition of the need for scientists to bridge the gap between complex scientific advancements and public understanding. As the scientific community navigates these tumultuous waters, the intersection of policy, public engagement, and scientific innovation will be crucial. The current climate serves as a reminder of the fragility of research funding and the potential consequences of political decisions on scientific progress. Looking ahead, it is clear that countries willing to embrace and invest in the migration of top-tier talent could not only enhance their own scientific capabilities but also contribute to a more resilient global research landscape. Ultimately, the future of bioscience may hinge not only on the retention of talent within the United States but also on the collaborative efforts of nations to foster an environment where scientific inquiry can thrive. As scientists seek new opportunities and as public interest in innovative technologies grows, the global scientific community must work together to ensure that the next chapter of research is one marked by inclusivity, support, and shared knowledge amidst a resurgence of interest in alternative treatments for serious illnesses. Ivermectin has emerged as a controversial contender in the ongoing discourse surrounding effective therapies for COVID-19 and cancer. Originally developed as an antiparasitic medication, this drug has seen a dramatic rise in prescriptions during the pandemic despite widespread scientific consensus regarding its ineffectiveness against COVID-19. Recent endorsements from public figures have only fueled the flames of misinformation, prompting health experts to reiterate the importance of relying on scientifically validated treatments. Since the onset of COVID-19, ivermectin has been touted by some as a potential remedy, paralleling the hype that surrounded hydroxychloroquine. A study indicated that prescriptions for ivermectin surged tenfold above pre-pandemic levels despite the lack of credible evidence supporting its efficacy for the virus. The U.S. Food and Drug Administration (FDA) has consistently advised against its use for COVID-19, emphasizing that the drug is only approved for specific parasitic infections in humans and animals. Reports of serious adverse effects from self-medication with veterinary formulations have only compounded the FDA's warnings. The conversation gained renewed vigor following a January episode of The Joe Rogan Experience, during which actor Mel Gibson claimed that ivermectin had cured several friends of stage 4 cancer. His assertion, broadcast to an audience of over 10 million, drew immediate backlash. The Canadian Cancer Society swiftly countered Gibson's claims on social media, denouncing the spread of misinformation as dangerous and irresponsible. Experts have echoed these sentiments, noting that while ivermectin has shown some promise in early studies related to cancer, comprehensive clinical trials have yet to demonstrate its effectiveness as a treatment. Despite the prevailing scientific stance, legislative efforts in several U.S. states are pushing to make ivermectin available over the counter. Arkansas has already legalized its sale without a prescription, and similar measures are being considered in Georgia and Texas. The push for accessibility raises concerns among health professionals about the potential risks associated with unregulated use of the drug, including serious side effects and drug interactions. In the realm of cancer, treatment research has explored the potential of ivermectin to inhibit tumor growth in laboratory settings. However, these findings have not translated into successful clinical outcomes in human trials. Dr. Suzanne Arnold, an associate director at the Markey Cancer Center in Kentucky, articulated the caution surrounding ivermectin, stating, "I know of no reports of clinical trials that yielded successful results in humans with cancer." This sentiment was echoed by Dr. Peter P. Lee, chair of the Immuno-Oncology Department at the City of Hope Comprehensive Cancer Center, who noted that while promising results were observed in animal studies, human trials are necessary to establish efficacy. The intersection of public health messaging and alternative medicine is complex, particularly when misinformation can lead to detrimental health decisions. Experts emphasize the need for rigorous clinical trials and evidence-based practices to guide treatment decisions. The FDA maintains that the current clinical trial data do not support ivermectin's use against COVID-19 in humans, underscoring the importance of prioritizing scientifically validated therapies. Looking ahead, the ongoing debates surrounding ivermectin and similar treatments highlight a critical juncture in public health discourse. As misinformation continues to proliferate, the role of health authorities, media, and the scientific community will be pivotal in navigating these discussions to ensure that patients have access to safe and effective treatments. The focus must remain on fostering a well-informed public that can differentiate between anecdotal claims and scientifically validated evidence, ultimately guiding individuals toward the most effective therapies available. As the world grapples with the urgent need to address climate change, the chemical industry, a significant contributor to global carbon emissions, stands at a crossroads. Recent research from a team led by Professor Xiaonan Wang at Tsinghua University sheds light on a promising path forward, harnessing artificial intelligence (AI) to drive decarbonization efforts across multiple scales within this energy-intensive sector. Published in the Technology Review for Carbon Neutrality, the study examines how AI can enhance efficiency and reduce emissions from the microscopic to the macroeconomic levels, providing crucial insights for policymakers and industry leaders alike. Decarbonization in the chemical industry is not a straightforward task. It involves complex processes that require innovative solutions. The research highlights the potential of AI-driven multi-scale smart systems, which can significantly improve existing mechanistic models, streamline operations, and promote resource conservation. At the microscopic level, machine learning techniques assist in material design and performance predictions, which are vital for developing new materials with lower environmental impacts. However, the researchers caution that data reliability remains a challenge, potentially hindering progress in this area. Moving to the mesoscale, AI-driven process modeling accelerates the application of decarbonization technologies within industrial settings. Despite this progress, scaling up digital integration remains a formidable barrier that must be addressed to realize the full benefits of AI in the chemical industry. At a macro level, the study emphasizes the importance of industrial symbiosis strategies that link chemical production with external markets and environmental factors. Technologies like digital twins allow for real-time operational adjustments, optimizing both production efficiency and environmental performance. Despite the promising advancements showcased in the study, the application of intelligent technologies in the chemical industry remains largely confined to the research phase. The authors point out that effective cross-scale modeling is essential for connecting experimental innovations at the molecular level with practical applications at the industrial scale. Moreover, the journey toward full-scale industrial implementation is fraught with challenges encompassing technical, economic, social, and ethical dimensions. Issues such as data security, infrastructure compatibility, AI interpretability, workforce displacement, and regulatory considerations must all be navigated carefully. The research underscores the necessity for interdisciplinary collaboration and multi-stakeholder engagement to overcome these challenges and expedite the chemical industry's transition to carbon neutrality. As the authors conclude, integrating AI and digital technologies across various scales can foster a more efficient, sustainable, and low-carbon future for the sector. In a parallel development, Florida International University (FIU) has announced an expanded partnership with CodePath, an organization dedicated to enhancing computer science education and career readiness for students. This collaboration aims to develop the next generation of AI-native engineers and technology leaders through a series of workshops, mentorship opportunities, and a cutting-edge curriculum that aligns with industry needs. With over 1,000 FIU students already benefiting from CodePath programs since 2020, this initiative is expected to further enhance students' competitiveness in the field of computer science. Michael Ellison, CEO and co-founder of CodePath, expressed enthusiasm about the partnership, stating, "Our expanded collaboration will further integrate industry-aligned curriculum into FIU coursework and expand career pathways." The partnership includes a new for-credit course on technical interviewing skills designed to equip students with the necessary tools to succeed in competitive job markets. As both the chemical industry and educational institutions like FIU explore the transformative potential of AI, the implications of these developments are vast. By fostering innovation and collaboration, they pave the way for a future where technology not only drives economic growth but also actively contributes to environmental sustainability. As we look ahead, continued advancements in AI and its applications across diverse sectors will be crucial in addressing the pressing challenges of our time. In a remarkable leap toward harnessing the power of nuclear fusion, China's Huanliu 3HL3 tokamak reactor has achieved a groundbreaking milestone by reaching ion temperatures of 117 million degrees Celsius and electron temperatures of 160 million degrees. This achievement, termed dual 100 million degrees, represents a pivotal step in controlled nuclear fusion, mimicking the processes that fuel the sun and offering a glimpse into the potential for a nearly limitless energy source. The HL3 reactor, located in Chengdu, is designed to confine superheated plasma using powerful magnetic fields, facilitating the fusion of hydrogen isotopes, deuterium and tritium, into helium. The energy released during this fusion process holds the promise of providing clean and sustainable energy, a goal that has eluded scientists for decades. Our experiment has achieved the dual 100 million degrees milestone, along with a major leap in overall fusion performance. This means China's fusion research is entering the burning plasma phase, stated Zhong Wulu, the chief designer of the HL3. During an interview with state broadcaster CCTV, Zhong emphasized the significance of this achievement, noting that this is the first time a comprehensive suite of heating control and diagnostic systems, developed entirely in China, has been successfully deployed in a fusion experiment. These systems now rank among the best in the world and have helped set multiple records in China's fusion research, he added. This advancement not only marks a significant national achievement but also positions China as a key player in the global quest for practical fusion energy. The HL3 reactor is part of a broader collaborative framework supporting the International Thermonuclear Experimental Reactor ITER, the world's largest fusion experiment currently under construction in France. The collaboration is open to international teams, and recent experiments in Chengdu have drawn participation from countries including the United States, France, Japan, South Korea, Portugal, and Thailand. Such international cooperation underscores the global interest in overcoming the challenges of nuclear fusion. As researchers continue to refine their techniques and technologies, the implications of achieving sustained nuclear fusion are profound. Success in this area could lead to a future where energy is not only abundant but also environmentally sustainable, significantly reducing reliance on fossil fuels and mitigating climate change. However, the path to making fusion a viable energy source remains complex, requiring further advancements in technology and a deeper understanding of plasma physics. Looking ahead, the results from the HL3 reactor will likely inform ongoing projects worldwide, including ITER. As nations collaborate and share knowledge, the dream of an operational fusion reactor that can provide clean energy to millions may be closer than ever. The fusion race is on, and with milestones like these, the prospect of tapping into the power of the stars is becoming an increasingly tangible reality. In a remarkable stride towards a long-sought scientific breakthrough, researchers at Caltech have unveiled a new superconducting state that could bring humanity closer to realizing the dream of room-temperature superconductors. The discovery of Cooper pair density modulation (PDM) marks a significant advancement in our understanding of superconductivity, a phenomenon that has eluded scientists since its initial discovery over a century ago. Superconductors, materials that exhibit zero electrical resistance, have been pivotal in developing groundbreaking technologies from magnetic resonance imaging (MRI) machines to fusion reactors. However, the vast majority of known superconductors operate only at extremely low temperatures, typically nearing absolute zero. This limitation has stymied their widespread adoption in everyday applications. While some materials like certain copper oxides can superconduct above 130 Kelvin, they still require impractical cooling methods that hinder their integration into modern technologies. The quest for a room temperature superconductor has long been dubbed the holy grail of material science. Despite numerous claims of breakthroughs in recent years, none have withstood rigorous scientific scrutiny. Yet this latest research, detailed in a paper published in the journal Nature, offers hope. The PDM state, while not a direct path to room temperature superconductivity, provides critical insights into the mechanisms that underpin superconductivity itself. Understanding the mechanisms leading to the formation of superconductivity and discovering exotic new superconducting phases is not only one of the most stimulating pursuits in the fundamental study of quantum materials, but is also driven by this ultimate dream of achieving room temperature superconductivity, said Stephen Najperj, senior author of the study. This highlights the dual nature of the research, both a fundamental scientific inquiry and a practical endeavor aimed at technological advancement. The study reveals that when superconductors reach their critical temperature, they form Cooper pairs, electron pairs that move through the material without resistance. These pairs are influenced by vibrations in the atomic structure known as phonons. Nadia Mason, a condensed matter physicist at the University of Illinois Urbana-Champaign, elaborated on this phenomenon. These electrons pair up over distances that are larger than the scale at which they'd be hitting atoms. So if you imagine a road that has a lot of bumps in it, electron pairs lift themselves up above the road so that the bumps are irrelevant to them. The new research delves deeper into the concept of energy gaps within superconductors, suggesting that these gaps might vary across a material. This led to the hypothesis of pair density waves (PDWs), which theorize that gap modulation occurs across varying wavelengths. The Caltech team's work with an iron-based superconductor has identified the smallest modulation wavelength aligning with atomic spacing in the crystalline structure. The observed gap modulation, reaching up to 40%, represents the strongest reported so far, leading to the clearest experimental evidence to date that gap modulation can exist even at the atomic scale, stated Lingyuan Kong, the lead author of the study. While this breakthrough does not immediately translate into a room temperature superconductor, it lays essential groundwork for future explorations. The team anticipates that the PDM state might extend beyond the iron flakes analyzed in this study, potentially unveiling new phenomena in other materials. This could eventually lead to the development of room temperature superconductors, a goal that remains tantalizingly close yet persistently elusive. As the scientific community continues to unravel the complexities of superconductivity, the implications of these discoveries extend far beyond theoretical interest. The realization of room temperature superconductors would not only revolutionize energy transmission but could also pave the way for advanced quantum computing networks, enhanced magnetic levitation technologies, and numerous other applications that could redefine modern society. The journey towards this monumental achievement is ongoing, with each new discovery inching us closer to a more efficient technological future.